using water to cool is not the only way. It's just the most convenient way, right? Yeah, well, superconductor can definitely help, but they will still try to pack as much processing power as possible. So one way to solve that problem, okay, is fusion reactor, right? So you use a fusion reactor, you power up the power center. All the wasted heat is used to distill water. So now, Los Angeles has fresh water. They don't need us to divert your water from Northern California. So you now solve a few problems at the same time. And of course, that fusion reactor is going to be on a Navy, carrier, okay, aircraft carrier. So, in case of emergency, the carrier can just detach and go on its own mission and do whatever it needs to do. But, during peacetime, it will dock, at, say San Diego, and then you'll be part of the grid. That would be kind of funny, right? Yeah, you have a floating power center, and then the wasted heat from the data center is used for water distillation because you're going to use salt water, to for cooling purposes, and we can expect the price of salt to go all the way to the bottom because it's basically free. Yes. What? Sorry. Yeah, but they're fission based, not fusion based. Yeah, so we want it to be fusion based so that we don't have to deal with the toxic waste that lasts like what. We're getting there, right? Exactly. Yes. Well, because all they need is for the aircraft carrier to be along the coast. They don't need to go all the way out, in the middle of the ocean. They also have a cruise ship, that follows the entire group because there's no dining facility on the carrier itself. So if you want to eat, you have to go to the other ship. Yes. Okay. All right. So we're gonna start the lecture. Let me start the recorder first. Okay. It doesn't hurt. Oh, okay. It's already started. So so what I'll do first is to kind of repeat the lab on Tuesday. Okay, so this way, people who could not complete the whole thing, I will release the file so that this way you have the baseline for today's lab. Okay, so today's lab is based on the file from Tuesday. Okay, so I finished grading the submission on Tuesday already. So we'll go ahead. I normally use Linux, but I'm using Windows right now in a virtual machine just so that I can demonstrate how to use Windows. And I hope the two videos that I sent out earlier in the announcement, I hope all of you have watched that video, especially people who have not used the command line interface before. So one of that video is going to be super helpful to help you with navigating on the command line interface. And then the other one is useful if you want to use the test driver to test your circuit before you turn it in. Now, is that needed? No, not really. Okay, you don't have to test your circuit before you turn it in. The only downside is if you don't do that, you may not know whether you're going to get full score for your submission or not. Okay, so that's the only difference. Yes. No, I give partial credit. I'm nice, but for the time being, everything is a little bit conditional. Alrighty, so let's go to the CMD, okay, or it's known as command prompt in Windows, but otherwise, generally speaking, it is known as a command line interface or CLI. So once you get there, okay, it opens up a prompt like this, and huh? Because we don't need all the extra crap from PowerShell, and some people may not have PowerShell installed on their computer yet, so it's really not needed. Well, if I wanted that, I would have used Segwin. which we are going to do later on in the semester. All right. So typically, when you download a file like logisim310.jar, it is going to be in your downloads folder, and it would be convenient to do everything in the same folder. Okay, so not counting the organization of your files. We'll just assume that for now we put everything into the downloads folder. I'm not going to explain the commands like cd because it is in the video. Okay, so people who do not watch the video, watch it. Okay. So now here I can use dir, to look at all the files, and logisim310.jar is here. So the way to run it is java-jar, and then the path to the file name, which in this case, because it is in the same folder, I don't need to do a whole bunch of slash or backslash to get to the file in a different folder. And that's why that's hence the convenience of putting everything in one single folder. So when your command line interface is using that same folder as what we call the PWD or the no CWD, which stands for current working directory, then you don't have to specify the path using the slash and the backslash. Yes, go ahead. Yep. Yep. So if you're using a Mac, the slash would be in the opposite direction. If you're using a Mac or Linux, the slash would be opposite to what I use here. But at this point, I don't need to use the slash. All right. So when I press the Enter key, we get into Logisim, and it takes a little bit of time because I'm running on a virtual machine right now. So here is Logisim. I'm going to recreate the circuit that that you were supposed to create on Tuesday. So I would do it, in a relatively quick way and not really fully explaining every little thing. So we need power. Okay, so stash power over here. And I'm going to increase the magnification. Zoom control is not what you would expect, which is the middle button just kind of scroll that little wheel. It is over here. Okay, this is the how you control it. Unfortunately, the projector is not cooperating. Let me see if I can make it cooperate because the left hand side is cut off a little bit. So I'm going to do an auto and see if it will adjust. Nope, not really. Okay, we are missing a little bit on the left edge here, but it will still work. So this is zoom control, kind of click it up to zoom in and click it down to zoom out. So we have the power, we have ground, and then we have to use a bunch of transistors. Okay, so I'm gonna pick one first. This is a P-type transistor because we can see there's a little bubble here. Um, and the orientation can be adjusted a little bit just so that it's easier for me to place it later on. So I wanted to face, it's facing east right now, and I need to rotate it one more time, so it's going to be facing south, like so. And this is one. I need the other one. Control D can duplicate, so this is duplicate. And after you duplicate, you can move the duplicate by dragging it around. And I'm just trying to make it look a little nicer. That's all. And with this one, you have to use the mirror, to kind of turn it the other way, which is gate location. So use the other option, but you don't have to. It just make it look a little bit nicer. And now we're gonna have to create two N-type transistors, down below. And when I was grading this, some people did not use the right kind of transistor, and therefore it didn't work for all possible cases. So this is an N-type transistor. I need this to rotate counterclockwise. So if I'm going to east, this is going to have to face north, and I need one more of these. Okay, Control D is duplicate. It just creates another one. So I'm going to place it at kind of where I need it. Another one kind of goes over here. And now I just have to draw, the actual connections, the wires. So there we go. Uh, Alrighty. So now we need the input pins and the output pins. So This is the best place, to pick up an input pin, because it has all the right configuration already. So it's really I would recommend just using that, and also the same, for the output pin. And both of these need to be 8-bit wide, so we need to go to data bits and turn it into 8. Oops, 8. There we go. And same over here. Turn it into 8, like so. Um, so now we need a splitter so that we can, split the input into two output pins, and then merge, you know, into merge one into 8 bits, on the output side. So the splitters are here. The splitter has its own video, inside the lab to explain how to use it. Some people probably did not notice there is a video to explain all of that. That's okay. That's so the bit width is 8. So the bit width of a splitter has to do with um, the merged end. Okay, the merged end, the split end, those are the two different ends. So when you specify the bit width, that is specifying the merged end. In other words, in total, how many bits are we dealing with? The fan out is, basically specifying the number of split end in this case. So right now I have two, split end, but you can control that. Okay, you can control that to be all the way up to 8 split end, where each bit has its own output. But in this case, if I want this to look nice, I only need the fan out to be 2. And whenever you change this, Logic will automatically try to reassign the pins, which is not necessarily in the way that you want it, okay, which is okay. So the way we want to configure this is bit 0 is going to the top pin, which is correct already. Bit 1 goes to the bottom, and all the other bits on the merged end will not be on the split end. So you have to specify all of those to be none, like so. And then we are pretty much done with this particular splitter. The other splitter looks about the same, so I'm going to be lazy. Do a Control D, duplicate this particular splitter, kind of move it on the other side. We'll deal with that later. And then we just stash it over here, make a connection to here, and then make connections from here to right here. And the same is going to go to one of the N channel or N transistors. This one is going to go to this one here. And I'm going to route it around the whole thing to go to the other side like so. Okay, it's up to you. Okay, whether you want to make it look nice and then you have a lot of crossover wire, it doesn't really matter as long as functionally it is the same. All right, so this is the funny part, because now you can use it kind of as is, but it's going to make the circuit look kind of ugly. So if you want your circuit to look kind of nice, like the one that I put into the lab, then you want to change the direction. So you want to go back to the control here and do a 180. So make it face west, and you want the fan out to be just 1, okay, to make it look nice. There we go. And then you turn off all the other bits. In other words, we only want bit 0 to be available to the merged end. Otherwise, everything from the split end is not going to go to the merged end, like so. And then we just kind of stash this all the way here. And then I'm just aligning things a little bit. And then make a connection here. And make a connection here. And oh, okay. That was not non-functional. It's just, I just wanted to look nicer. There we go. So I think the circuit is done. Okay, so let's test it. Okay, to test the circuit, you have to use the poke tool. This is called the poke tool. And only bit 0, this is bit 0, and this is bit 1. Only those two bits are used to actually control the circuit. And 1 1 gets a 1. That is not. Hmm. right, so that's a 0. Oh, right, you're correct. This is connected. Thank you. So I made a wrong connection. This segment of the circuit, should not be here. Oh, okay, fine. Let me see if I can just move this segment over a little bit. There we go. You can move just a segment, and then I can delete this segment here because this is supposed to tap between the N and the P transistors. So that would be a good place. There we go. All right. So now we can test the circuit a little bit. All right. So 1 0 is a 1. That is correct. And then 0 1 is a 1. 0 0 is a 1. 1 1 gets me a 0. Okay. That's a NAND gate. Okay. Very good. Thank you. Cool. So now that this is all done, we go to the appearance. Okay, there are two ways to get there. You can go to project, I think. Nope. Go to edit. I cannot remember. There's a way to get to the appearance right there. Edit circuit appearance and make sure that it looks good. By default, it should look good already. But a few people used two input pins instead of one input pin and one output pin, so it's not going to look like this. Okay, so that's why it did not work for a few submissions. Okay, so when this is all good, we save the file, and I think according to the instructions, you're supposed to save the file as NAND2. I did not deduct points, for people who turn in something that is not named NAND2. It's okay, not a problem. All right, so that's done. So when that is all done, now you can use the test driver to test the circuit. So let me illustrate how to use the test driver. It is in the video already, but I might as well just kind of demonstrate right now since I'm already here. So you go to the companion to the lab, which is where you turn in the file. So for people who basically got it done already, the first thing I would do is to turn it in. But if you, so this is the test driver, you download it. And now it's downloaded. All right. So according to the instruction, what you need to do is to rename or make a copy of your circuit as reference.circ. Okay. You can do it in using a Windows manager, or you can just do it on the command line. Okay. So if you do it on the command line, the command is really just copy, or if you're doing this in Mac OS or Linux, it's CP, okay, because they like to abbreviate, all the names. But if you do it in Windows, it's just copy. So now I have to remember where I saved that file, and I cannot remember. Okay, and I'm switching in the wrong window too. Let's see. When I save the file, it's probably in Documents. Okay, so this is also a good opportunity to illustrate how I can find my file. So I can do a dir, which is listing the content of a folder, but the folder is documents, which is at the same level as downloads. So I need to move up once and then move down to documents once. So the way to do that is to use two dots to move up and then a backslash because I'm using Windows to specify, okay, where do I go from the parent folder? And then we specify documents and tab will autocomplete. And now we can see what is in that folder. Ah, okay, my file is over there. So we can now just copy that. Okay. nan2.circ as reference.circ. Obviously, you can also do all of this in File Manager so that you can just kind of, click a file, Control C, copy, go to another folder, Control V, paste it over there, and then change the name. Okay, but I'm a command line, interface kind of person, so I like to do everything through the command line. So now we have all the files here. Okay, we have logisim 310 over here. We have reference.circ. We have testdriver.circ. So this is where you type the really long command. Okay, so it's java dash jar logisim 310.jar. This will start up logisim. But we don't want to start up Logic Sim in graphical mode or in GUI mode. We want to run the whole thing in text mode. So now we have to specify which circuit we wanted to run, which is our test driver circuit. And then when we specify dash TTY, it means we are not going to go into GUI mode. So you say table because we want the output to be in a table form that is tab separated. And I think that's it. Press enter key, and now we have the output that is actually also quoted in the assignment description. Yes, yes, yep, you can do that too. So redirect, is like this. Okay, it's a greater than symbol. It allows you to capture the output or the standard output from a particular program into a particular file. So in this case, if I want it, I can say test.txt because that's what it is. It's just a regular text file. So now you would see no output from the command, but now I have a file called test.txt. Then you can use various tools to compare the text file to the one that you can possibly download from the assignment itself so you can verify the two files are the same. All right. So are there any questions? Okay. Yep. Test driver. Well, the reason why we're copying to reference is because test driver is looking for a component called reference. So if you don't rename it, there's a way to make it, use Nantu instead of reference, but it will just lengthen the command even longer. So this is an easier approach to accomplish the same thing. Yep. Yep. hmm So when you turn in either one because Nantu and reference are actually the same file, so you can turn in either one. So that's pretty much a quick redo of the lab on Tuesday. Are there any questions? Yep, that is a good question. The question is, why are we using 8-bit input and 8-bit output? It's just me being lazy because I want to use, I want to do one single test driver circuit. And later on, there will be some test circuit that needs more input bits and more output bits. So I just wanted to do one, and this is it's if you specify too many bits, it's okay. But if you design it, it doesn't have enough bits, and I have to redesign the whole test driver. So it's just me being lazy. Yes. Yep. The test driver is a little bit different, because the test cases that I want to feed into the test driver is different depending on what the circuit is supposed to do. That is correct. All right. Very good. Very good questions. Any other questions? All righty. So one thing I do recommend is, even for the labs, you might want to take notes, okay? Because there are things that you learn in one lab that will be reused in a different lab. So all the techniques, all the tricks of using Logisim, you probably want to take, make some notes of that, so that when you need to do something again, it's like, oh, how do I do that? Just look up your own notes, and there it is. All right. So let me, before I forget, let me post this in the announcement so this way everybody can have my solution as a reference point for today's lab. I will talk about today's lab in just a little bit, but let me post this first. So this is the solution for Tuesday's lab. And oh, no, 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 scroll back up. In a very typical fashion, see attached, and then attach it. So I will attach this from the documents folder and to and publish. There we go. So now everybody has a copy of my solution that I just worked on, and you're going to need that if you do not have yours up and running. You're going to need this file to get started with today's lab, which is a good lead in to, what are we going to do today? And that is not a pinky question. Oh, there's no reaction to that one. So maybe you guys are too young to know what is pinky. Pinky in the brain. And what does Pinky ask every episode at the beginning? Yep. And what do you think is brain's typical answer? Exactly. hmm There's that show, and then the other show that I really like also is SpongeBob. My brain is simple, okay? I just like simple stuff. SpongeBob is good. Alrighty. So we're going to finish up the chapter or the module that we have already started the other day by describing why we introduced the NAND 2 circuit. So the NAND 2 circuit, okay, let me just go to the circuit first so that you guys can remember what we were talking about. This circuit, okay, which is also the thing that I worked out a little bit earlier. So why did I introduce this circuit as the very first thing in this entire semester? Well, kind of because that's all you need, okay? In other words, if you have a circuit to perform the job of NAND, the rest we can handle. You go like, wait, but this is not even a usual, operator. You have learned negation, like the exclamation point. You have learned conjunction, which is ampersand ampersand, and you have learned or disjunction, which is the double bar from Cisp 360 as the only available logical operators. So we don't even have NAND as an operator in that class. So what we'll do is to basically take a look at how you can emulate the other logical gates from a single NAND gate. So we're going to scroll all the way down here. NAND is all we need. We don't need anything else. So the first thing is we'll get the notation first. Okay, NAND is I'm using the up arrow as the NAND operator, and I claim that the negation of x is the same as x NAND x. Okay. In other words, the negation of x is also denoted as exclamation point x in C++ syntax, x with an over bar in computer engineering notation, or slash x in electrical engineering notation. So depending on your occupation, you can encounter the concept of logical negation in different notations. Is that okay? So I just tell you something, okay? I just asserted something, which is the equality between logical NOT of x and x NAND x, which is the negation of AND. So what are you gonna do? What do you normally do? You just write it down, okay, and then you say, I'm gonna study this and memorize this. Well, okay, that might be what you usually do in your other classes, but in my classes, I encourage you to question it. In other words, are we sure this is right? Can tech be wrong? The answer is yes, tech can definitely be wrong. Not intentionally, but sometimes just accidentally. So how can you verify this on your own? That the negation of x is really just x NAND x. How do you do this independently? Yep, you can test it. Yep. But you can also just use what we call the truth table, which is a fancy way of let's test every single value of x and make sure that the negation of x turns out to be exactly the same as the negation of x and x. Okay, so let me illustrate what I mean by that because I just said a lot of things. I'm not a very verbal person or auditory person, so I need to actually see it. I need to see it in order to process it. So I'm going to use notepad here or mouse pad to do this. Okay, so the question is, no matter what x is, how do we know? Okay, I'm going to put a question mark here to ask, is it really the same? Okay, that's what the question mark is emphasizing. Is it really the same as this? Okay, so now that I have presented the question in a format that is in CISP 360 compatible, format, how would you answer that question? Yes. Mm-hmm. Mm-hmm. Yep. So you're trying to reason through the whole thing, right? You're using basically algebra, but without actually referencing, Boolean algebra. That is correct, okay? Because we can do it that way, but we can also do it the kind of dumb way, okay? Because tech really likes the dumb way, and hence, and that's why I like, SpongeBob, okay? The dumb way is like this, okay? If x is false, what is not x? Well, technically it's not zero, but we'll just call it one, okay? So now you move on here, and then you try to answer this question. Well, let's just say that we don't know Boolean algebra. We do not know that x and x is really just x, okay? We don't know all of that because I've never taught that. So you say, okay, x is false. What is false and false? False, okay? And then what is the negation of false? True. Okay, very good. So we are just applying everything that you should have learned in CISP 360. So now that X is true, what is true and true? True. What is not true? False. Okay, very good. So now you look at the second and the third column, or the middle and the right column. Do they seem to have exactly the same value for every single row? Okay, well, we're done. That's the proof. Okay, so in Boolean algebra or in Boolean operators, if you want to prove one expression is equivalent or the same as another expression, you can always use a truth table. This is a truth table and it's really, really useful. Is that okay? All right. So now we move on to something that is a little bit more complicated. So the next one is regular and. This is the mathematical symbol of and, which you otherwise know as ampersand ampersand. So now I'm trying to say that x and y is the same thing as x NAND y NAND x NAND y. Okay, so how do you prove that? Because I just gave you a statement. I gave you an assertion, and you should always doubt my assertion. I don't know how you treat your other professors, but with me, you always doubt. You always say, I'm not sure whether you're telling me the truth or not. So how can you prove this? Well, let's go back and look at the truth table approach. The answer is yes, you have learned enough to do this already. So now we ask, okay, here's x, there's y, okay? When x is false, y can be false or true, okay? When x is true, y can also be false or true. So these are the four possible cases of what values x and y can assume at any particular time. Does that make sense? Okay. So I hope you guys are taking notes, okay? Because this is a technique that is not described in the module itself, and yet it is useful in many, many ways, not just in this class, but also in CISP 440 and anytime you have to deal with Boolean expressions. So if you're not taking notes, I'm a little worried. All right. Okay. All right. I just need that part to be recorded so later on I don't have to say anything. Things like told you so. Okay. So now we just work out the regular and, which should take you like 5 seconds. Okay. False and false is false. False and true is false. True and false is false. True and true is true. Because one way to look at conjunction is the conjunction is true if and only if both sides of the operator are true. Okay, so that's a fairly easy one to work out. So now we look at the NAND thing. Okay, so I can just use the NAND thing, but instead of using the NAND thing, I'm going to retranslate the whole thing into operators that you are familiar with. So we are referring to this part, but I'm going to spell it out in C++ notation. So x NAND y itself is the negation of x and y, and we have to basically NAND this thing with itself. So that means we're going to have to AND this with itself and then negate the entire thing. There we go. All right. So are we okay with how I just expanded this notation, which is using NAND as an operator, to the much more clumsy way of using negation and regular AND? All right. So we're going to work this out. Okay. Well, okay. I'm not going to work this out. I'll let you guys work it out. Okay. And sometime off of class two. This is one way to burn up those 2 hours for every hour in this classroom. So you might want to jot down a little bit of notes and say, okay, Tech just gave us, some activity to do, and I'm going to have to spend some time to work this out. Okay. It's not going to take you a lot of time. I mean, it looks really tedious, but once you get a hang of it, it's like, not a problem. And I would even give you the C code or the at least the pseudo C code to do it. You can just say if int x equals to 0. This is C++, okay, because you can declare integers from inside. X is less than 2 plus plus x, and then you do the same thing for y. Okay, y equals and then you specify the expression. For those of you who use C++, it's going to be a C out. So you just have to C out, and I'm just going to be super lazy here. Copy, paste, done. Now, if somebody is just going to copy and paste this code into an editor and expect it to run as this, I'm sorry, you might need to retake CISP 360 because everything needs to be inside the function. So you put it inside main in order to run it. Okay. All right. So I'm giving you everything that you need in order to kind of test this one, either by hand or using a code, piece of code to do it. So I'm going to move on. So now the next one is OR. So OR, which is X or Y, this is the mathematical symbol for OR, which is also known as double bar in CISP 360 or C++. It boils down to be X NAND X NAND Y NAND Y. Okay. So this time I'm going to leave it up to you to create the C++ expression that is going to represent X NAND X, the whole thing NAND, Y NAND Y, the entire thing. Okay, but the template is the same. Okay, it's not really that much different from the one that we had before. Is that okay? I think being able to verify, what I claim to be true on your own using the tools and using, just a piece of paper is a good practice in many ways. Okay, one, you actually get to understand the material a little bit more, okay, because you're actually doing some hands-on stuff. Some people learn a lot more effectively when they do something, okay, when they work it out on paper or they work it out on code. And other people can just look at something and go like, okay, that's good. I just have to think about it a little bit, and then I can absorb it. Okay, so it depends on what works best for you, in terms of learning, but you have to process it, okay? Unless you have already taken this class, somewhere else, and you have to take this class just so that it appears on paper in your transcript, okay? But sometimes I get those students too, and they don't really have to take notes in this class. All right. So are we okay so far? All right. So assuming that you are convinced that the NAND operator can be used to implement logical negation. The NAND operator can be used to implement logical and the NAND operator can also be used to implement logical OR. That means that's all you need. All those operators, negation, conjunction, and disjunction in C++, they're all not necessary. Okay, the programming language could have just given you NAND as an operator, and the rest can be derived from NAND. Yes, the sideway. You mean this thing here? That's logical not, which is the same as exclamation point. All right, so let me show you where or how it is defined. It is defined up here. If we are talking about the negation, note that the negation of x, which is what this symbol is representing, is also denoted as exclamation point x. So it is kind of implied here that this operator is the same as just the exclamation point, which is logical not. Which is also a good place for me to remind the class reading ahead is useful. Okay, because if you were to read ahead of time, then a lot of this stuff you already have it in your mind or possibly even in your notes. So the only reason you come to class is to make sure that your understanding is correct. It gives you a chance to ask questions. It's like, well, my understanding of what you wrote is this, okay, but I just want to clarify that it really is the case. Okay. Are we okay so far? Okay, all right. So we are going to move ahead to the next module, which is about the base conversion. Okay, what you're going to do in today's lab is what we just talked about, using the NAND operator or NAND gate to implement NOT and OR. Okay, that's kind of, but from a circuit perspective, not from the expression perspective. Okay, so it gives you yet another hands-on opportunity to kind of do something in order for the concept to sink in. All right, so we're going to move on to base conversion, which is further down after this is your actual lab tonight. So let me just unhide it first, and I'll give you guys the access code at the end of the class. So this is the next module. And as you can see, I just talk about the modules in the order as they are listed in the Canvas shell. So there is no reason why people cannot read way ahead of my actual lecture. I also have all my recording of all the previous semesters. Well, I shouldn't say all, sometimes I forget, but most of it are recorded already. So if you want to kind of look into the future, like what I'm going to talk about in 2 weeks, you can always go back to the previous semester, kind of figure out the date of what is equivalent to the second or the third week, and then watch the video. Then you have a little bit of you know what I'll be talking about. Now, do you have to understand everything from a pre-recorded lecture? The answer is no. But if you want to get an idea of what where the class is heading, that would give you a pretty good idea of where the class is heading. Okay, so all of those are resources available to you. All right, so now we are going back to value, numbers, and the bases. So before we talk about this, I'm going to use my mouse pad here to kind of give the class a few challenges. The first one is, do you think you can work at McDonald's or fast food place because it would involve giving your customer an exact change using the least number of coins and bills? So what do you think? Do you feel confident that you will know how many coins, what coins and how many bills, then use the smallest possible number to give the customer an exact change? Okay? And the amount of time does not even matter. Okay? I just need to know whether you know the method, to do it, whether you can do it like like that, or you kind of like, okay, I need to count a little bit here. It doesn't matter. As long as you know the method and the approach, we're good. So I'm seeing a lot of thumbs up, nodding, and stuff like that. Okay, because when I talked about this with my colleagues at the CISP, with other CISP professors, they told me you cannot assume your students know how to do that. I go like, how did they graduate from high school? I don't mean it in a bad way, but in a very pragmatic way, okay? Because that's really basic math, okay? You may not know how to turn that logic into code like that. That's okay, okay? That's kind of why I'm here, okay? We talk about coding and the approach of doing things, but knowing how to do it by hand is important because that's kind of a sense of math, okay? It's not even algebra; it's a sense of mathematics, and that's why it is important. All right, so I'm going to give you guys an example. Let's just say that I need change for $17, and I'll make this something that is easier to work with later on. So $17.75. So instead of giving the customer 1,775 pennies, what should I do? Start with the largest denomination that is less than or equal to this amount. Okay? Yes. Say again? Well, so the way we do this is the change that you need to give back to the customer. Yeah. So this is not the money that you need to charge, but this is the amount of money that you need to give back to the customer because the customer gave you a $20 bill to buy something that is only worth $2.25. Okay? Which is sometimes annoying, but sometimes people do that, right? Okay. So the way we do it is like, okay, so I, one way to do this is to list all the common bills and coins. Okay, we'll just have an inventory of all those. $50 bills. Okay, I'm gonna go the other way. Penny, um, a nickel, a dime, quarter. Well, let's not do half dollar because they're not common. So we're gonna only use the common ones. So we got dollar bill, $5 bills. I know there are $2 bills too, but they're also not common. So $10 bills, $20 bills, $50 bills, $100 bill. No one's gonna, bring a $100 bill to a fast food place, so we can stop there. Okay. First of all, do you notice any regularity here? Let's look at the multiplier from one row to the next row. Okay, so we'll go ahead and work out the multipliers, okay, from one row to the next one. All right, so this is 5x, from the one before. This is a 2x from the one before. This is not even a whole number. It's 2.5. Okay, well, is it? Yep, okay. And now we have a 4, and now we have a 5. Then you go like, oh, okay, so the pattern is going to repeat again. 5, 2, 2.5, and 4. 5, 2, 2.5, and a 4. No, there's no regularity. 2, 2, back to 2.5, and then back to 2. There's no regularity. There's no repeating pattern at all. Okay? And yet, you have mastered how to do this already. Is it is that a fair statement? Okay? So give yourselves a pat on your back and say good job. Okay? Because base conversion is far easier than this. Okay? And I'll illustrate why that is the case. Okay? But we'll go back and solve this entire problem first. So given that is the amount, then you go like, now do I have to start with the largest bills? The answer is no. I can actually start with the smallest bills too. But we'll go ahead and start with the largest one first. So we start with the largest one. You go like, that is stupid. That is kind of stupid. That is sort of stupid. But we got one of these. Okay. So after $10 are gone, you have what? $7.75. Okay. So we're gonna need a one, and then we're gonna need two of these, two of the $1 bills, and then we're gonna need three quarters, and we're done. Okay. So the rest are all zeros. So if you think, yeah, I can totally work this out. Okay, I can even work this out faster than tech. Cool. Okay. So now we go like, what does this have anything to do with base conversion? Well, let me propose a new currency system. Okay, so the new currency system, tax proposal, is we have an eighth of a dollar, we have a quarter of a dollar, we have half of a dollar, we have $1, $2, $4, $8 as bills, $16, $32, and what do you think the next one's going to be? 64. Very good. So you guys are noticing the pattern, okay? And I'm gonna, just kind of talk a little bit out of the context of this class here. Noticing the pattern is important, okay? Because that is what programming is all about. You're trying to generalize, how to do something into a pattern, okay? Once you know the pattern is, translating that pattern into code is really just translation. That's the easiest part of the job. Knowing what the pattern is the hardest part, okay? But you guys just did a good job, okay? You just noticed what the pattern looks like. So let me just put the amount up here again, so just so that we can look at it. So we have $17.75. So we're going to use the same approach, okay? We'll say, oh wait, before we do that, let me illustrate one thing first. What is the multiplier to get to a row from the one before? Two, two, two. I think you guys get the point, okay? They are all twos. So if you have a cousin from a foreign country, just immigrated into the United States, and you have to explain the currency system, which one do you think is the easier one? I would say the second one. If I were a politician, this is the first thing I would propose. Change the currency system so that it is binary, because every single amount here is a power of 2. Okay, but let's work it out first, okay? Because you guys do not seem to be convinced that this is also easy to work with. So we're going to use the same approach. Start with the largest bill, okay? We got 0. We don't need a 64. We don't need a 32. We need a 16, right? Because there's 116 in 17.775, okay? But after the 16 is gone, we only have $1.75 left. So we don't need an 8. We don't need a 4. I know this is really tedious, but I just want to kind of go through the whole process. We need a 1, okay? Because 1 plus 16 is a 17. And then we get to the half. Yep, we need one of those. And we need one of those. And we don't need one of those. So the way we figure out, how many of each denomination is really the same. The logic is the same. But this is actually far easier than the other one because there's no division involved. There's only comparison. Is the remaining amount greater than or equal to this amount? If so, give me 1. If not, give me 0. There's no division. If Sorry? Or exactly, because modulus is a form of division. You're just focusing on the remainder instead of the quotient. So it is a form of division. But you're correct. That's a correct observation. There's no mod. There's no division. Just imagine how math can be a lot easier in elementary school if we just taught base 2 numbers instead of the crazy base 10 numbers that we deal with. What do you think is the size of the multiplication table in base 2? Technically, it is 4 because you have 0 times 0, 0 times 1, 1 times 0, and finally we have 1 times 1. How long do you think it would take an elementary school student to memorize that entire multiplication table? Yes. Yeah. Okay. I have to make one disclaimer. Before they were contaminated by base 10. Exactly. The reason why we look at this as strange is because we have been contaminated by base 10 for years. Okay. And that's why when we look at something other than base 10, we go like, ew, that looks ugly. Okay. But if you were never exposed to base 10, this would have been like, this, I would settle for this than base 10 any day. Okay. But at the same time, we are looking at a binary number now, okay? So I'm going to put a little dash here because this is the divide between the powers of 2 that are negative and the powers of 2 that are non-negative. Is that okay? So you go like, but why is that boundary important? Yeah, go ahead. Yep. But this line of dashes is important because that's what the quote unquote decimal point is about. The job of a decimal point is to separate the digits that tells you the number of non-negative powers of whatever base you want to use from the quantities of negative powers of whatever base you want to use. So that's why that line is important. So if I look at this entire thing, and I can convert it now into a base 2 number, it is 0.11010 in base 2. I just did base conversion. Is that okay? Cool. All right. So if I can convert, so now we have to go back to some kind of more fundamental question, which is there a difference between a numerical value versus a number? So consider those two terms, a numerical value versus a number, and what is the difference? That is correct. Okay, so Ilya, do you want to add to it? Nope. Okay. So I'm going to illustrate that point. Okay. So if I were to ask you how many fingers I'm holding up, okay, but 9 is just a word for this quantity. The quantity itself has no name. Okay, it is just a quantity. But when we need to communicate with another person of what quantity we are talking about, then we need a representation. Okay, 9, N-I-N-E as a word is how we spell out, to mean this quantity. Okay, if you are to write it out, okay, what are we going to use? Okay, in base 10, because we have been poisoned by base 10, that's what we write. Okay, as a base 10 number. But we can also write this as 10001 in base 2. So now we look at this whole thing here and go like, that's crazy. Okay, well, it's not crazy. 1 of 1, none of 2, none of 4. Oh, I got it wrong. That's why you should always question my answers. Okay, whatever I tell you, always kind of go like, really, Tack? Because that's what I would do to myself. Okay, so we have one of one, none of two, none of four, one of eight. So now we have one of eight and one of one, add them together, and that's the quantity of nine. Yes, because we read base 10 number the same way. Okay, well, okay, so all right, so let's go back here to something that is actually in the notes in the module already, but I'm going to do it anyway. So we'll go ahead and take a look at this quantity, which is a base 10 number. Okay, so there's no trick to this. So I want to say, okay, what exactly is 179.05 as a base 10 number? You guys would go like, that's crazy. I mean, we know what this is, but I'm going to give you, like, okay, let's look at this as 100 plus 70, whoops, 70 plus 9 plus 0, point 0, plus point 0.05. Would that be okay? Okay. But what I have done is I have isolated the each digit in the original number into its own term in the summation. Is that okay? That seems pretty obvious, right? Okay, well, that's fine. Obvious is not a problem. So now I'm going to make this even more obvious. You go like, how can we possibly make this more obvious? It's 1 times 100 plus 7 times 10 plus 9 times 1 plus 0 times zero point 0.1 plus 5 times zero point 0.05. 5 times zero point 0.01. There we go. Is that okay? So what have I done? I have re-expressed each term in the addition into a digit, a single digit in base 10 times a power of 10. Okay? So I will go one step further just so that the pattern becomes super duper obvious. 1 times 10 to the power of 2, I'm going to use the character means to the power of in this case, plus 7 times 10 to the power of 1, plus 9 times 10 to the power of 0, plus 0 times 10 to the power of negative 1, plus 5, whoops, 5 times 10 to the power of negative 2. Whoops. Yeah, there we go. Okay, is that okay? But do you notice a pattern? Every digit in a number is representing the quantity of a particular power of the base. And that power is relative to the position of that digit. The purpose of this point here is to tell us where is the digit that tell us the quantity of 10 to the power of 0? Right here. That's the job of the decimal point. And for those of you who came from Europe, that's the job of the comma, because the way comma and the period or the decimal point are used is opposite in Europe. Is that correct? Yep. Okay. So okay. So this is what a number really is. Okay. What a number really is every digit is telling you the quantity of a power to of the base, and the power itself is relative to the position of the digit. Okay, so now we need a way to designate the digits now. Okay, so now we have to look at this number here and we ask, okay, 17905. Okay, and I need to name the digits. This is called digit zero. It is digit zero because 9 is telling us the quantity of 10 to the power of 0. Okay, otherwise known as 1. 7 is digit 1 because it's telling us the number of tens or 10 to the power of 1. The 1 in that number is digit 2 because it's telling us the number of hundreds, which is also known as 10 to the power of 2. So what about the other side? You go like, what about this 0 here? Well, we call it digit negative 1. We call this digit negative 2, and so on. So are we doing okay so far? With how we basically label every digit with a certain integer so that we can refer to, oh, we mean that digit over there. Is that okay? All right. So now we're going to go the opposite way. I'll give you something that is not in base 10. I'll give you a number that is not in base 10, and then you're going to have to tell me what quantity it is representing. So let's see if you guys can do this. So we'll do it the opposite way. So we'll say, 1, 2.3, but it is in base 4. Let's try a base that we haven't done with, we haven't used before. Okay. 12, 2.3 in base 4. What quantity is it representing? So if this is the first time for you, I would suggest you to kind of list all the powers of 4 that are in use over here. So what is a power of 4? That's an easy one because that's 4 to the power of 0. Okay? And then we go like 4 itself is also a power of 4 because 4 is 4 to the power of. Okay? So using that particular trend, what do you think is the next one? Nope. 16. And then the next one, 64. Okay. What about the other way around? What is above the 1? In other words, what is 4 to the power of negative 1? Hmm? It's known as a quarter, but it's also known as 0.25 in decimal. And what is before that? It's 0.25 divided by 4. And I'm going to have to think about this a little bit. 625, like that. Okay. Okay. Uh-huh. That's how we do it. So now tell me how many of each do we need? Okay, we'll start with this one. Do we have how many 0.0625 or 4 to the power of 4 to the power of negative 2 do we need in this particular number that I gave you? Okay, you go like, well, Tag, you didn't specify. Well, I kind of specify because it's kind of implied that there's a whole bunch of zeros to the right hand side and there's a whole bunch of zeros to the left hand side. Okay, so let's try to answer this question again. What is the quantity of 1/16th in this number? 0, because digit negative 2 is a 0. Okay, where's digit negative 2? Well, we always home in to digit 0 first. Digit 0 is the one that is immediately to the left-hand side of the decimal point. This is digit 0. This is digit negative 1. This is digit negative 2. Ah, we have none of those. Is that okay? All right. Okay. Well, I have just shown you, enough to answer the next question then. How many quarters do we have? Yep. And how many ones do we have? 2. And how many fours do we have? And how many 16s do we have? Exactly. Oh, okay. So now the question really boils down to, can you multiply and add in base 10? I sure hope so. I sure hope so. So we have 0.75 plus 2 plus 4. Okay. So 4 plus 2 is 6. So this quantity here is representing 6.75. Mm-hmm. Is that okay? So let me just write down the answer here for you guys, to kind of try to absorb it. Okay, so basically we're saying 12.12. I shouldn't say 12 because 12 implies it is in base 10. So 12.3 in base 4 is 6.75 in base 10. It is the approach that is important. Okay, the most fundamental concept in all of this discussion is what makes a number a number. What is each digit doing as a part of a number? The position of the digit and the base are both important as well. Okay. Do we have any questions at this point? Yep. Not multiples, powers. Yep. So each digit, based on the position of the digit relative to the decimal point, is telling you which power of the base it specifies, the quantity thereof. All right, you're good. All right. So the question is, this is really a question. Okay, sometimes I ask a question only, kind of it's a formality. This time it is not. Okay, this is a real question. So the question is this abstract or not? Is this too abstract for you, or is it okay? I can see where it's going, and I'm grasping the concept just fine. Yep. Okay. All right. Okay. So reading the notes can be very helpful here because the notes actually cover most of the examples that I talked about. Not exactly the same value, but it gives you exactly the same point. Okay, we are dissecting the number, and then we use a summation to kind of indicate, oh, what is the value of a base 10 number? Now, the important part here is most people are, if they did not read the whole thing, the first time they read the equation itself, it's like, what is D0? Well, that's why you don't jump to just the equation. You always want to read sequentially. So if you were to read sequentially, I specify here we use the notation. Oh, such a bad spelling here. What is a negation? Notation. Okay, I'll fix it. We use the notation d of I to represent the digit that indicates the quantity of 10 raised to the power of I, which means it is digit I of the number. So d of I specifies digit I. So if d of I is digit I, then we multiply d of 0 or digit 0 by 10 to the power of 0. We multiply d1 by 10 to the power of 1. We multiply d negative 1 to 10 to the power of negative 1, and so on. I mean, it expands on both sides. Okay. So the summation notation is just an easier way to denote the entire thing. So is the concept of the summation notation okay with the class? Or yes? Okay. Yep. Go back to, you mean the notepad? Yep. Because okay, first of all, we start with the 2. That's digit 0. It tells us the quantity of 4 to the power of 2. That's what I've been saying. Digit 0 is the quantity of whatever base you're using raised to the power of 0. D of 1, digit 1, is the quantity of whatever base you're using raised to the power of 1. Digit negative 1, which is on the other side of the decimal point, tells you the quantity of whatever base raised to the power of negative 1. The position of the digit correlates to the power that you need to raise the base to. In this case, what is the base? Exactly. So is that okay? All right. Well, now we know what you're going to spend the 2 hours for each hour of the lecture to be doing, right? Because you need to absorb this, okay? To absorb this, you can ask Chat GPT, okay? You can say, okay, how do I interpret 12.3 in base 4? I'll bet you it knows the answer. Okay, let's give it a try. Okay, I don't want to give you information and it turns out to be not true, but I'm fairly sure that it does. All right, so we'll go ask ChatGPT, and this is the usual model, which is 4.0, and we just ask it. Okay, what is the value of 12.3 in base 4? Okay, and please explain. Okay, you don't have to type please, but it's nice to do it. Yes, it's nice to be to the AI. I did. Oh, wait, wait, wait. I did not write the prompt backward. It interpreted it backwards. Oh, okay. Okay, that's one way to interpret because where you put the parentheses is the question, right? Because the implicit parentheses that in my mind, okay, is 12.3 in base 4. There's parentheses around this one, so I'm looking for the value of open paren 12.3 in base 4 close paren. But ChatGPT did not understand the priority of the operators, so it would say the value of 12.3 parenthesized in base 4. So it gave me exactly the opposite of what I need. Okay, so let me ask the question again, and let's see how we can re-ask us the question. So I am given a number in base 4, 12.3. I hope this is clear enough. Can you show me the decimal value of this number? Please show the steps. Okay. I hope this is clear enough. This really goes back to something that I talked about in the previous class. Sam Altman said what? The most important skill is to know what question to ask. And apparently also how to ask the question. How to evaluate the answer and go like, okay, I need to rephrase that. Yes, it is implicit that it's going to be in base 10. Nope, this is wrong too. Oh, this is the other one, right? You're right. Oh, okay. Okay, this time we got it. Okay, there we go. Yay. So yes, ChatGPT can definitely help clarify concepts. But guess what? This is a fully in-person class. Your exams will be on paper without electronics. So do not over rely on ChatGPT. Okay, that's just okay. Generally in life, that's what you want to do because we are already seeing a decline of critical thinking skills and problem solving skills because some people are over relying on AI to basically do all their thinking. Um, it's just like muscle. I don't care how much muscle you're born with. If you do not do anything, if you just sit around and watch TV, you're going to be a couch potato. It doesn't matter what your genetic, it doesn't matter whether you have an advantage genetically speaking or not. So you need one more thing before we leave here because you need to get started with this lab, right? So I'll give you the access code or the access code. It is Nandroid. It is Android with an N in front of it. And if you don't get the pun, it's okay. I won't take points off if you don't get the pun. I'll see you guys at the lab. Alrighty.